Alright, so concept 3 of our force will be free fall. Okay, so what defines a free fall? Okay, so imagine you're on Earth and you do an experiment where you suck up all the air from a chamber. Okay, so you have a chamber of vacuum, and you decided you want to drop a ball from the top of the chamber to the bottom of the chamber. So this object is said to be undergoing free fall. Okay, because the only when it's falling, right, the only force that's acting on this ball is the weight mg. Okay, yeah. So of course, when the object experiences only its own weight, the acceleration itself is about 10 meter per second square. So how do I derive this acceleration of 10 meter per second square? Actually, it's derived from the Newton's second law. So F is equal to ma. So remember, your F is your resultant force, right? And inside this so-called vacuum chamber, the only force acting on the object or the ball is the weight itself. Okay, and just nice, the weight is also your resultant force. Okay, because there's nothing to cancel out, there's nothing to add up. So the only force is your weight, mg. Okay, and you notice that mg is equal to ma. And we can cancel away the m, right? Because m is the same, left hand side, right hand side can cancel. So a is equal to g, where g itself is equal to 10 meter per second square. Alright, so now we derive, actually your acceleration is equal to your gravitational field. Okay, so this is what we call the Einstein first equivalence principle. So Einstein first equivalence principle states that actually this may be just a bit of sidetrack. Actually, there's no such thing called the gravitational force or gravitational field. Gravitational field derived from the acceleration, right? So this is something you can digest, you can ponder when you are free. All right. Okay, so let's move on. Okay, if I plot my velocity time graph of this object, I will have a straight line graph. And remember, for the gradient will be 10 meter per second square. Right? But of course, in a real life situation, we need to put in air resistance, because air resistance is all around us. Right? Okay, so let's move on. So an object experiencing air resistance is called non-free fall. Okay, because there's not only the weight acting on the person or the object, there's also like many other forces like air resistance, so on and so forth. Okay, so let's take a look at this diagram. So I have 4 diagrams, right? So this man, a man of about 83.3 kg, dropped from a helicopter. Okay, so at the start of the jump, just at the instant where he jumped, the only force acting on him will be the weight, 833 Newton, and there will be no resistance. Why there's no resistance is because at the instant where he just fall, the speed of the man is 0. Since you are not moving, right, you are stationary instantaneously, right, there is no air resistance also. Okay, because in order to have air resistance, you need to be moving. Right? Okay, so the only force acting on the man is the 833 Newton. And if the man is about 83.3 kg, what is the acceleration at this instant? So let's calculate using F equal to ma. F equal to ma. So F is equal to 833. Your m is equal to 83.3. So if you calculate correctly, your acceleration is equal to 10 meter per second square. Okay, so you must be wondering why when you're not moving but you are accelerating at such a high rate, right? So later I will tell you why. Okay, after when you just jump, after a while you move, right? you fall through the air. Okay, so your speed increases. As your speed increases, means that your air resistance increases as well. More and more air is acting on you. Okay, so on the side of the person, you will see like many air molecules or particles opposing the motion of your man. Okay, so now the air resistance is about 350 Newton. If you use your Newton's second law, F equal to ma, the m is still the same, 83.3, but your resultant force is no longer 833, is 833 minus 350, so you get about 483 Newton downwards. So your m is about 83.3 kg. So if you calculate, you should get an acceleration of about 5.80. Okay, so the acceleration is falling already, is dropping. Okay, so diagram C, you reach an even higher speed. So now your speed are even higher, so I draw a longer arrow, hence your air resistance will be even higher. Okay, so if you calculate using F equal to ma, your resultant force is about 133 Newton. So resultant force 133, your mass is still 83.3. Okay, so your acceleration will be about 1.60. Okay, meter per second square. Okay, let's move on to the last part of the journey. So now his velocity increased until such that the air resistance is equal to the weight. So there's no resultant force. F equal to ma, so where F is 0, your A is equal to 0. So at the last part, your acceleration is equal to 0. Okay, so there's actually a special term for the last part of the journey. Since your A is 0, right, means that your velocity is constant. So they name it as terminal velocity. Okay, so they name it as terminal velocity. So if I plot my velocity time graph, you'll see that it's actually a curve. It's like a curve, right? So at the start of the journey, the slope is quite steep. So of course we know that at the start of the journey, the acceleration is about 10 meter per second square. Because if you still remember your kinematics, right, the gradient of a velocity time graph is your acceleration. Now after falling for some time at part B, diagram B, right, your slope will be smaller because the acceleration is smaller. Okay, of course, for part C, the slope even gentler, right? For part D, this is where your slope is equal to 0 because your acceleration is equal to 0. Hence, your slope must be 0. Alright, okay. So just take note of the very start of the journey, where you just jump, you are stationary instantaneously. Although your speed is 0, but your acceleration is 10. Okay, this is a bit counterintuitive because normally when we say, when you are not moving, definitely your acceleration is 0, right? That is because we are dealing with horizontal motion. Horizontal motions mean I'm moving left to right or right to left. Okay, so if I'm not moving from left to right or right to left, means that I'm really not accelerating. But for this case, is dropping, right? Is falling. Is from up to down. Okay, so this person up to down. So in this scenario, there's a gravitational force acting on the object. And this gravitational force is in the same direction as your motion. So that's why now the scenario is a bit different already. Okay, so we must, at the start of the journey, v equal to 0, but a is equal to 10. Right, so this is up and down. So when we are dealing with up and down, the physics is a bit counterintuitive already. Right? Okay, so let's move on. Yeah. So this is basically the explanation. Right? Okay, so what happens when the person jump with a parachute? Just now there's no parachute, right? Now there's a parachute for him. Okay, so look at all the different diagram. At the start, same thing, you just fall, you just jump, right? So the only force acting on him is mg. Alright, at the start, of course, if you use your so-called second law, right? Newton's second law. Newton's second law, ma is equal to mg, and you can cancel away the m. So your a is equal to 10. Right? So as you move faster through the air resistance begin to increase as well. Okay, so of course your acceleration will decrease, right? But not to 0. Okay, because so air particles will begin to form on his body already to oppose him. Okay, then if you look at the graph, okay, there will be a point where before he open his parachute, he will reach the first terminal velocity. How do I know when he open his parachute? This one is actually, if you look at the speed time graph, is actually very prominent one. After reaching my terminal velocity right here, the first terminal velocity, where my weight is equal to your air resistance, suddenly, if you look at your diagram, suddenly the speed decreases rapidly right here at this portion, 20 seconds. Okay, so I can conclude that at this particular point, this is where he opened his parachute. Okay, because something must happen. If not, how come the speed decreases so drastically? Okay, so when he opened his parachute, the surface area of the parachute is quite high, right? So of course there are more air particles opposing the parachutist. Okay, so the air resistance now is bigger than your weight of the parachutist. Okay, so that's why you decelerate. Actually, you're moving downwards. So this is your motion, right? You're moving downwards, but you decelerate. So that means your air resistance, your resultant force is upwards. Okay, so your acceleration is upwards. Okay, so after that, you of course you decelerate further until where you reach a very low speed. You go back to equilibrium again, because when you reach a very low speed, you notice that if you compare the third diagram and the third and the fourth diagram, the air resistance from third to fourth diagram decreases. Why is that so? Alright, because when you open the parachute, you will decelerate very drastically until maybe right here, right? Until this part, okay, where your air resistance will decrease also. Okay, because at the fourth diagram, your velocity decreases, hence your air resistance decreases. So just remember, what determines the amount of air resistance is basically your speed. If it's directly proportional, okay, so air resistance is directly proportional to the speed. If your speed decreases, your air resistance will decrease also. Okay, so that's why at the fourth diagram you reach equilibrium again. And what do I mean by reaching equilibrium? Your air resistance now will be the same as your weight again. Okay, so at this portion you will reach your second terminal velocity. Alright, so second terminal velocity, same thing. Your so-called mg is equal to your air resistance. Right? Then of course, then after that, you continue, then after that you just land. So you land, of course, you stop moving. This is really stop moving. Alright, so this is for the parachute case. So let's take a look at, so this is the schematic, so-called explanation for all the different parts. Alright, okay, so for checkpoint 11, a parachutist is falling at terminal velocity. Alright, so terminal velocity means acceleration is equal to 0 without her parachute open. She now open her parachute. What is the direction of her motion? So I need to determine the direction of the motion and what is the direction of her acceleration immediately after she opened her parachute. Okay, so we need to determine the direction. Okay, so when you are falling, whether you open your parachute or not, you are still falling downward. This is something that we need to know. You cannot like open parachute and then suddenly you fly, you increase, you fly upwards, right? Cannot be. You just slow down in your descent. Okay, so the direction of motion is still downwards. So answer is either A or B. Okay, now I will need to determine the direction of the acceleration after opening the parachute. After opening the parachute, okay, because of the very big surface area of the parachute, a lot of air particles will form right here to oppose the motion of the parachutist. Okay, right. So now all the so-called the upward force, air resistance, will be bigger than the weight of the parachutist. Okay, so this will be upwards right here, air resistance. So in terms of resultant force, we know the air resistance, let's just say I put some value to help us analyze better. If this man has a weight of maybe 800 Newton, the air resistance will be about maybe 2000 Newton. Okay, and you will see that my air resistance now is bigger than the weight. So there will be a acceleration upwards, or there's a resultant force upwards. Since there's a resultant force upwards, from our Newton's second law, right, we know that your acceleration must be in the same direction as your resultant force. So your acceleration must also be upwards. So answer should be B. Okay, but just to elaborate further, although your resultant force is upwards, doesn't mean you fly upwards. You are still continue falling downwards. Okay, so this is what I want to put across. Alright. Okay, checkpoint 12 is a 2011 question. When his parachute is fully open, a parachutist fall towards the ground at constant speed. Under this condition, what statement is true? So constant speed must A equal to 0, right? So A, there are no forces acting on the parachutist. So this is definitely wrong. Okay, if they say there are no resultant force acting on the parachutist, this will be correct. But they say there are no forces acting on the parachute, this is it's a big wrong, because there is actually two forces acting on it. So one is your weight, the other will be your air resistance. Right? So two forces. B, the upward force on the parachute is equal to the weight of the parachutist. This is correct, because the resultant for option B, the other way of saying this is that there is no resultant force. So answer should be B. Okay, right. Okay, checkpoint 13. A parachutist of 80 kg is falling through air when he 80 kg, let me just label. When he opened his parachute, after parachute open, the total air resistance is initially 2400. So now they give us some value to play with. Okay, so this is the person, which is the weight, 800 Newton. Alright, and open the parachute, right? So just draw this, and we have a air resistance of 2400 Newton. Okay, what is the initial deceleration after the parachute open? So they want us to calculate the acceleration upwards. another way of saying it, or the deceleration also can. Okay, so same thing, F equal to ma. Okay, so my resultant force is upwards, but I don't know the magnitude, right? I can calculate 2400 minus away 800. Right, so if you calculate correctly, you should get 1600 Newton upwards. So let me label 1600 Newton upwards. So your mass of the parachutist is about 80. So your so-called deceleration will be about 20 meter per second square. Okay, so 20 meter per second square is right here. Okay, so answer should be B. Alright, so this is for your parachute terminal velocity.